Hey everybody! So in this video we're learning some more detail about sound waves and how they actually travel, as well as how to describe sounds in different ways. So these are the learning intentions you should learn in the video. You should be able to explain sounds in terms of volume and pitch. Then you should be able to explain what sound waves are in terms of compressions and rarefactions. And you should be able to list the speed of sound in different materials. In particular, solids, liquids, and gases. And we'll talk about that in a minute. Okay, but first of all, we've got two new keywords here, which are volume and pitch. And we do use these words in everyday language, particularly if you're a musician. So we should know that volume is just how loud the sound is. So if sound's got a high volume, we say it's loud. And then if it doesn't have a high volume, we say it's soft. But another way we can describe sounds is in terms of their pitch. And that's saying, is it a high-pitched sound, like screeching tires or someone screaming? Or is it a really deep and low-pitched sound, like a foghorn or a deep person's voice, or a person's deep voice? So, pitch. It's talking about, is the sound high pitch or low pitch? Alright, and here are some examples. So we can talk about the volume and the pitch for every single type of sound. So here is an AFL umpire, and when she blows the whistle, it's a really high-pitched sound, and it's really loud too because it can travel across the whole field. So we can say it is loud in terms of its volume, and it's got a high pitch. But then if you've got a little kitten meowing here, it's still high-pitched, but it's a really soft and low volume. So soft and high pitch. If someone's down here on the drum kit kicking the kick drum, that's a low-pitched sound and it's pretty loud. So loud and low pitch. And then someone walking just with normal footsteps on the carpet, it's low pitch, but it's pretty quiet. So we'd say soft and low pitch. So for every sound, you should be able to think, okay, what's the volume and what's the pitch? And those two words relate back to the actual sound wave, as we'll learn later. Okay, so here's sound wave. Here's a diagram of a sound wave again. And remember, sound waves travel through longitudinal waves. Longitudinal. And we need to be able to describe these two words to do with a longitudinal wave. So in a longitudinal wave, there's parts where the particles are spread out more, and we call those the rarefactions. So here in the rarefaction, the particles are spread out. And then the other part of the wave are regions where the particles are really tightly packed together, and that's called the compression of the sound wave. So particles are tightly packed. And remember that the overall wave is moving forwards in one direction. And it's really hard to picture, so we're going to have a look at a couple of simulations to see it actually in real time. So here we go, we've got a longitudinal wave, and we're using sticks here to represent the particles of air. So you can see each compression, I'm following it here with the mouse, the compression's moving from left to right. And so the wave, we say, is moving from left to right. And each rarefaction is also moving from left to right at the same speed. And so if we're standing at the end here, and we're receiving the sound, we've got a rarefaction and then a compression, then a rarefaction, then a compression. So it's alternating what's arriving at our ear. So the wave moves, but most importantly, each individual particle of air, it actually doesn't move very far. And it definitely doesn't move the whole way from left to right. So if you follow the red coloured particle here, all it's doing is vibrating back and forth. It goes up and then it goes back. And so every single particle in the air, it just moves back and forth a little bit, but that's enough to make the whole wave transfer a long distance. So the wave moves, but not the particles. That's probably the most important thing. So in this picture, the wave moves left to right, but the particles only vibrate, or only move back and forth. Okay, so that's using sticks to view it, but the more realistic version is with particles, because this is what makes up the actual air, or the solid material, whatever the sound's travelling through. So here, we're going to make a sound wave move through this lot of air particles here. So whatever's pushing the air, let's imagine it's a speaker. You can see it pushes on the air particles, they bump into the next ones, and then they bump into the ones beyond them. So it's a constant chain reaction of particles bumping into each other, and that causes the compression to move all the way along. And then we've got another compression here. So the compressions push each other along, and then the rarefactions follow along afterwards. So you should be able to picture and explain how sound waves actually move. Okay, the last thing is to compare the speed of sound now in different materials. We learnt last time that the speed of sound in air is about 1,200 kilometers an hour. And this is common because if you yell out to someone across the oval, that's the speed the sound travels through the air. But actually, that's the slowest speed that sound travels at. It's way faster in other materials. So the average speed that sound travels through liquids is about 5,000 kilometers an hour. 4 times faster. Way faster. So if you're underwater in a pool, you can scream out to someone underwater, and if they're underwater, they can hear you a lot more quickly than if you yelled out through the air. And then in solids, it's even faster again. So this is just an average. But on average, sound goes through a solid material at about 10,000 kilometers an hour. Way faster. So the numbers here aren't super important, but you should realize that there's a clear pattern that sound moves slowest through air and gases, moderately through liquids, and then the fastest through solids. Okay. So you should be able to explain pitch and volume, and explain sound waves, and then list the different speeds of sound.